G'day, Glenn Morris here from the Smart Energy Lab, and I'm here on day 2 at All Energy with Russell French from Amped. Now, there's probably a bit of a joke here, but you must be feeling amped.
I am completely amped. This is the first time that we've exhibited at the conference. I've been here for many, many years, but we're loving it. We're meeting with customers, new and old, and talking about projects and talking about our products.
So let's start with, what is Amped? Tell me about the company.
Amped is from Colorado, USA, formed in 2007. Basically, we have sites all across the world, and we're in 15 countries now. We specialise in DC-DC conversion technology for large-scale solar plants. So utility-scale solar plants, where the missing link in the equation between the PV modules, the battery, and the inverter.
But don't inverters already have an MPPT?
They do, and we disable it because it's not an efficient way to do it. Where you want to do your MPPT is down at the PV modules. So you want to do the MPPT down there, and then do your electrical mismatch loss correction at the PV modules, and then you get the most efficiency out of the system. And we're talking about like 4 or 5% extra energy yield by doing so. And over the life of a system, say 25 years, that could be millions of dollars, tens of millions of dollars, or sometimes $100 million extra revenue.
So are you saying you can retrofit this? So you've got an existing system and you can grab another 5% out of it?
Well, you can retrofit. So on a brownfield site, you can retrofit, or you can do a greenfield site, like a brand new project. But we can often go into old sites and help with energy sag. So when the voltage is sagging on the system, boost that up again, get it to where it needs to be, and then attach a battery to the system. Or we go on a brand new project from day one and do a DC coupled solar system. And there's various architectures within DC coupling. But what we're seeing right now is that the market is moving away from the older styles of AC coupled or even like BESS only systems to hybrid DC coupled solar.
Well, let's unpack that a little bit. So if you've got a pure solar system with no storage, this will improve the efficiency of the solar. But when you add storage, the typical way is to convert DC to AC, then take AC and then charge the battery. So there's conversion losses. You're saying you do something different.
Well, if you have a look at versus an AC coupled system, so immediately if you go to DC coupled, that's at least 4.5% extra round trip efficiency improvement, if not 8 or 9% improvement. And the other thing is, on an AC coupled system, you have all these harmonic losses which then go out to the grid, which cause instabilities and those kind of things. So an AC coupled system has 2 points of connection to the grid, as opposed to 1 point of connection with a DC coupled solar system. That's more efficient. The other thing is, when you do all this grid modeling, so this large scale utility scale end of the market, you have millions of dollars of grid modeling that you need to do. With our system, there's at least 2 case scenarios less modeling that needs to be done, which means you're saving huge amounts of money to get the systems onto the grid. As we head towards the energy transition, we need to do rapid deployment of assets. So you're getting onto the grid faster, get your approvals faster for less money with 1 point of registration, which is it's just easier.
Right. So you're effectively putting the battery onto the PV.
Well, there's different architectures. So in a battery-centric architecture, where the battery is dictating the DC bus, everything follows the battery. The battery is a really stable source of voltage, and so we just follow the battery in that architecture. And so that's incredibly responsive for communications, and it's really stable on the DC bus. So we just follow them. Actually, reverse DC coupled or battery-centric architecture is from telecommunications from the 80s or 90s. It's a really old way of doing things that has been reinvented for large-scale solar.
Wow. Now, we haven't even talked about the product, but I think we're standing in front of it.
We are.
What's this?
That is the heatsink hub. This is an optimizer. So that's a 70 kilowatt optimizer. So really power dense device. This one is the 45 kilowatt unit. And so what we do is we put them at the string level and mount them to the torque tubes of the racking solution or the pylons, either fixed tilt east-west racking, or it could be a dual access tracker system. And we mount it right down at the PV modules. And by doing so, then we get the maximum power point tracking there. We get the mismatch loss correction of dealing with degradation of solar modules, as opposed to dealing with it at the centralized level. So when you do it at the central level, you have many more losses, and it could be 200 meters away, and you're not dealing with those issues right at the modules where they need to be. And the PV modules have a variable cloud impact. clouds come in and out and the voltage is unstable, the power coming out of the units is unstable, and we either fix that voltage really high and lower the current right down, and stabilize the whole DC bus, which then means that you spend less money on cables because you have low current. You pay for current in a solar system. So our device helps enable smaller cables, less combiner boxes, smaller DC switches, which means it's a lower cost up front.
I guess you don't often think about the cost of cables, but when you're doing a solar farm, that's a big component.
Oh my goodness. On a recent project, we're looking at really large projects. We helped lower the cost of cables from like say 17,500 lengths of cable to 4,500 lengths. We're talking like $8 million saving, US dollars saving on that project. Plus the combiner boxes on that particular project, we could take out some like 350 combiner boxes at $3,500 installed each. You're talking, over $1 million there, and that's just up front, let alone generating, because, we're so efficient, we generate, say, 5% more power or energy yield over the life of the system, and you're talking millions of dollars extra revenue to the asset owner.
Now, having these out at the array, what are the other advantages of having the array?
Well, one is that, they're under the PV modules, for starters. So they're shaded. We have them in deserts around the world, 45 degrees Celsius, continuous heat impact. So the heat isn't an issue with them. But having them at the array, they're going to be shaded under the array. So there's a lot of natural airflow happening already. And it's just far more efficient. You don't need a big centralized device that you have to pour concrete for. Then you have trenching to do. You need a crane to lift it in. These are like 10 minutes to install, plug and play. MC4 connectors, plug it in, screw it to the racking solution, and you're away. The other advantage is that if you need to swap one out, there's an issue, 10 minutes, unplug it, plug it back in. If you have a centralized DC-DC converter, what's going to happen is, if there's an issue, you could knock out 1 megawatt of the system. So 1 megawatt of the system is knocked out. Then it takes you 3 weeks to get another one to site. What does that mean for the asset owner? Loss of revenue and income, and that defeats the whole purpose.
So you can have a few spares just in case there's a lightning strike or something, and just
1% of spares on every project. Right. We just keep them on the site in a container or something like that, and so it's just fast. So the electricians and the guys on site love them, because then they can also do data monitoring down at the string level. So the data monitoring gives them the deep insights into what the PV modules are doing at the string level, as opposed to maximum power point tracking at the inverter, hundreds of meters away, and you could have 13,000 PV modules on one channel, and you're trying to figure out, which part of my array is not working? Let me see, it'll take me 3 days to figure this out. Electricians are running around all over the place. It just makes no sense. You want to be proactive and get straight to the heart of the problem.
So the granularity means that you can see per string what's happening. How does it communicate that?
The communication is wireless. So we have our own proprietary protocol, which is wireless back to a communications unit. Then it goes to the EMS SCADA PPC system wirelessly. Well, once it gets to our comms unit, then it's hardwired. And we're also just about to implement Zigbee mesh network. So even more effective communications, and it just makes it easy. So again, plug and play, get the wireless connected, and you're off and running.
It's a perfect application for Zigbee, like a solar farm, open field, line of sight, but it's a big area that you've got to cover, but you're repeating it with a mesh network.
You're repeating with the mesh network, really proven technology, stable as well.
So have you got projects in Australia these are being utilised on?
We do. So we have Australia's first reverse DC coupled project that we have up near Brisbane. So won an award for that project. So it's very first of its kind, called Latitude. And so that's installed. We have another project under construction right now, which is still under wraps. We have orders that have been placed this year, and those construction's already beginning on those projects. We have a design went on a huge 400 megawatt project up in Queensland called Chumaru, which is getting developed right now. And there's a second part of that, which is another 400 megawatt. So we're talking, well over 1 million solar panels on these projects. And they're huge. But we've done it around the world for countless years anyway, so it's not our first rodeo, and we have 380 megawatt projects in Chile and projects in Japan and Europe, and we've been doing this a long time.
So are you knocking on the door of existing solar farms and saying, would you like another 5% of that?
Well, basically, I mean, it's a no-brainer, really. Like, as you move away from AC coupled to DC coupled, I mean, this is not some, fantastical, something innovative that hasn't been proven. We've been doing this a hell of a long time. It just makes more sense. And what happens in Australia is there's a lag in projects. So as they get designed, say 2021, 2022, those projects are only just getting implemented now. So the technology that was available then is dramatically different than what's available in 2025, 26, right? So now for developers and engineers making their decisions on technology, there's just much more advanced ways to do it. And it's already, the first movers are already moving in the market. So you look at these huge developers like Edify Energy. I mean, they're looking at gigawatts worth of projects. The Capacity Investment Scheme, CIS, from the Australian government just approved 3 projects for them. And these huge, like 400, 500 megawatt projects. And they're not the only ones. There's Gentari just announced a 243 megawatt hybrid project on the east coast of Australia, DC coupled system.
Yeah.
So every system in Australia is going to have a battery on it moving forward on the large utility scale, grid forming. And it just makes so much sense, and that's what the government's getting behind.
Wow. So you know this already, but a bit of a fun fact, this is an Australian invention at MPPT, but found in every inverter and now in amps, string level, module level optimizers. It's amazing.
Absolutely amazing, and it's crucial. It's crucial to these solar systems. I mean, it has to do the maximum power point tracking effectively, but the key is you've got to do it at the PV modules. Forget this centralized, older, outdated, technology approach. It's got to be done at the PV modules where the variability is coming from the cloud, and that's what makes the most sense.
Well, thanks very much, Rusty. It's been great talking to you, and look forward to hearing more about Amped.
Thanks, Dan. Always a pleasure.
Cool.